Okay, so we will continue talking about linear momentum on to part 3. So we had discussed the impulse relationship, the fact that to change the linear momentum of an object, you need a force. And it's the force times the time which that force acts on the object that's equal to the momentum change or the impulse. Now we get into the law of conservation of linear momentum. Along with the law of conservation of energy, this is probably the second most important and insightful rule or law that science has ever discovered. So if we call them bread and butter rules, I guess if the conservation of energy was the bread, then this is the butter. And again, by the word conservation, what we mean by the word conservation here is not that we're trying to save momentum, but rather that we're dealing with an amount of momentum that stays the same. So again, the word conservation here is referring to an amount that remains constant. And the law says this. It says if no forces from outside the system act on the system, then the momentum in the system will remain constant, or in other words, will be conserved. Okay, so for example, one of the things that we talked about earlier in the course when we were talking about Newton's third law of motion, we talked about Robert Goddard and his vision of putting a rocket into outer space and propelling it in empty space. And we talked about at that time that the way we talked about it with respect to Robert Goddard is we said, well, he said that if object A puts a force on object B, and if A was the rocket and the exhaust gases were B, then if A put a force on B, then B puts an equal and opposite force back on A. And so we understood rocket motion from that perspective, right? And from that viewpoint. We can also understand it in terms of this law of conservation of linear momentum. Suppose we have a rocket here in outer space, okay? So there's nothing around this rocket at all. Nothing. It's out in empty space. Okay, so we're ignoring gravity and things like that right now. This rocket's out in outer space. It has a velocity of 0. It's got a mass m. And so the initial momentum in the system, as we look at it, okay, is 0, right? The momentum is 0. After the rocket fires its engines, if our dotted box here, if our system box is big enough, then that force of the engine, of course, exhausting the gases, is inside our system. That is, it did not come from outside the system, right? So those forces are internal. And so the rule is that if no forces come from outside, then the momentum must remain constant, which means after the rocket fires its engines, we need to still have 0 momentum in the system. Now, when the rocket fires its engines, we know, as we discussed before, that the exhaust gases are going to come out with some amount of speed, right, in the negative direction here, and we're going to have an equal and opposite force put on the rocket, which will cause it to be propelled in the positive direction with some speed, another different speed v. Okay, so remember, momentum's a vector. Momentum's a vector. So this is positive. This is positive momentum here that the rocket's carrying. The positive momentum of the rocket. Okay, and we've got some negative momentum for the gases back over this direction to the left. And so the overall effect here is that when we add these two together, when we add the momentum that the gas carries to the left with the momentum that the rocket has towards the right, we end up getting 0. Which means if we write this as an equation, the mass of the exhaust gases, right, the mass of the exhaust gases times their velocity, right, or even, if we just equate the magnitudes of the velocity or the magnitudes of the momentum, then the mass of the rocket times the exhaust gases speed equals the mass of the rocket times the speed that the rocket ends up moving with. Okay, and if you notice, this is quite an amazing result because we've got to the actual speed of the rocket without having to do any F equals ma type calculations, right? We didn't use energy conservation, we didn't use kinematic equations, and so this is again another tool that we can put in our arsenal of tools that we can use to solve problems. And that is we can get from, just knowing the mass of the exhaust gases and the speed at which they come out, knowing the mass of the rocket, we now get to the final speed of the rocket. So this is quite an interesting law, and it's throughout nature, and it's very powerful. And of course, it doesn't just apply to rockets in outer space. We could imagine suspending a rifle, for example, in the classroom from the ceiling, maybe from some strings here. And let's suppose it's loaded with a bullet. If we put a big dotted box around that and we say, well, what's the momentum in the system? Well, initially, of course, there would be no momentum in this system, right? The momentum in this system is 0. Okay. After firing the bullet, what we will find is that, of course, the bullet will come out with some mass m and move at some very high speed v, and it will carry momentum to the right. That's positive momentum, right? We also know that what happens if you've ever fired a gun is the gun, which is actually much more massive than the bullet, will have some kickback, and that recoil velocity or recoil speed, which is usually a smaller amount, v, is back the opposite direction, so that will carry some negative momentum. Again, if the initial momentum in the system was 0 and we conserve momentum because no forces come from outside our system, notice the discharge of the weapon was something that happened inside the system, right? There was an explosion of gunpowder inside the system, therefore no forces came from outside. Our final momentum of our system still has to be 0. So whatever momentum was carried forward by the bullet, an equal amount of momentum is carried backwards by the weapon. Okay, this is important because this helps explain, right, the same relationship. The mass of the gun times the speed at which the gun comes back has to be equal to the mass of the bullet times the speed the bullet goes forward. So if we shoot a lead bullet, which has, you know, some mass at a very high rate of speed, then we're going to have a fairly significant amount of momentum that has to be carried back towards the shooter. And so one of the things that you've probably found if you've ever shot a weapon or picked up a weapon is that they generally are pretty heavy. They're massive. And the reason for that is you want this mass to be large enough compared to the bullet so that the recoil velocity here, right, back towards the left, is small enough compared to the velocity at which the bullet goes forward. Because if this goes forward very, very fast, even with this being a modest amount, we have a significant amount of momentum coming back towards us as the shooter. So if the gun and the bullet were the same mass, if this mass and this mass were the same, then these velocities would be equal. And it would be just as dangerous to fire the gun as it would be to stand in front of the gun with the bullet coming towards you. So guns generally and weapons tend to be pretty massive. So let's take an opportunity here to practice this a little bit. And what I show here is Calculo, the physics boy wonder. And he has a mass of 50 kilograms, right? And he stands at rest on frictionless ice. Don't worry about how he's standing on frictionless ice. Of course, that would be impossible, really. But let's suppose he's able to do it, and there's nothing below his feet here that will resist his motion, okay? He catches a 10 kilogram medicine ball that's thrown towards him at 12 meters per second. So this ball is moving towards him at 12 meters per second. It has a 10 kilogram mass. Okay. Let's just kind of ignore, we know if we throw a real ball, it would kind of arc, you know, due to gravity, but we're going to ignore that effect. Let's just suppose the ball is going straight towards Calculo here. It's coming straight towards him in a straight line. And what I want to know is if he catches the ball, all right, if the 50 kilogram physics boy wonder catches this 10 kilogram ball moving towards him at 12 meters per second, how fast do he and the ball, after he catches it, move off to the right? We know momentum has to be conserved, and so I want to know how fast in meters per second do he and the ball end up moving to the right after he catches the ball. So at this point you may want to pause the video, work on that answer, and then restart the video to see how you did. So pause the video and work on this for a minute. Now, if you received an answer when you worked the problem out, if you got an answer of 2.4 meters per second, you're on the right track. You're close, but that is not correct. Take a look at the problem again and try it again. So pause the video, go back and look at your work, and see if you can see what you did wrong. Okay, now that you've had a chance to look at it again, hopefully you got the right answer. If you got an answer of 2.4, what you were doing was neglecting the fact that after Calculo catches the ball, he has 10 kilograms more mass than he did before he caught it. In other words, what we really have happening here is two objects, right, that become one object after he catches the ball. So if we look at the momentum before, it was a 10-kilogram ball moving at 12 meters per second to the right. Remember, momentum is a vector, so signs matter. The fact that this is a positive velocity moving to the right in our coordinate system is important. Calculo had 50 kilograms of mass, and he was not moving in our coordinate system, so he had zero momentum. So the total momentum in the system before he catches the ball is 120 kilogram meters per second. Again, there is no special name for that unit, so we might just say 120 units of momentum. Okay, after the collision, we know we must maintain the momentum. We must conserve the linear momentum. How do we know that? Well, again, if I put a big dotted box around my system, and there's no forces that come from outside my system, no winds blowing, no ropes pulling, then the momentum inside the system must remain the same. It can change, the amount of momentum of each object can change, but the total momentum of all the objects in the system will add up and remain the same overall value. So after Calculo catches the ball, okay, he catches it, then it's as if we have one object that has 60 kilograms of mass. And the question is, how much velocity does a 60 kilogram object have to carry in order to have the answer of 120 units of momentum? So it's a little bit like playing Jeopardy, if you're familiar with the TV show Jeopardy. It's like saying, well, we know the answer to the total momentum after he catches it. Total momentum in the system is 120, so what's the question? Well, the question is 60 kilograms times what equals 120. And so 60V equals 120 yields an answer of 2 meters per second. So after Calculo catches this ball, he and the ball will move off together, okay, at a velocity here of 2 meters per second. Now, in a lecture before our test last week, talking about impulse and momentum, I did make the comment that bouncing puts a bigger force than sticking. Here's an example that helps us understand that a little bit better. It's exaggerated a little bit to make the point, but let's suppose we have a 1 kilogram object moving at 6 meters per second, and it collides with a 5 kilogram object at rest on ice. So let's just make this a bowling ball. So let's suppose we have a 5 kilogram bowling ball at rest on like frictionless ice, and we've got a 1 kilogram object moving at 6 meters per second coming straight towards it. Again, same kind of rules as we did with Calculo. We're not going to worry about the parabolic trajectory of something thrown. Let's just imagine it comes straight towards the bowling ball. Keep it one-dimensional. That 1 kilogram object's moving at 6 meters per second to the right, and we want to know what is the velocity if, after the collision. But there's two possible types of collision here, right? I mean, we could have, what if we threw a piece of putty or a piece of clay at the bowling ball? That piece of putty is going to go to the right and just stick onto the bowling ball and become part of the bowling ball, and that's an example of an inelastic collision. But we could also be throwing like a super ball, a ball that is rubber that's going to bounce back. Okay, and so let's take a look at both of these situations and compare the momentum or compare the final velocity of the bowling ball in both of these cases. If you want to, you may want to pause the video at this point and try to work out the answer to each of these. Okay, so they both start with the same before picture. So if we have this situation before and it's a piece of putty, then the question is, what would be the velocity of the bowling ball at the end in that situation? Okay, and then the second question is starting with the same beginning situation, a 1 kilogram object moving at 6 meters per second, but now we're going to assume it's a super ball, and that super ball, after it hits the bowling ball, bounces back here at 4 meters per second in the negative direction. And so the question is then, what's the final speed of the bowling ball in that situation? So again, if you want to try that out, pause the video and try that out yourself. You can do that and then restart the video to see how you're doing. Okay, so let's see how you did on this. So again, we talked about the fact that it's a 1 kilogram object moving at 6 meters per second towards a 5 kilogram bowling ball sitting on frictionless ice. It's just going to slide after being hit, and that's our before picture. So the momentum before the collision happens, the bowling ball, of course, has no momentum, right? It's not moving. In order for something to have momentum, it has to have velocity in our reference frame, and the bowling ball does not. So all the momentum in the system is carried by this piece of putty, for example, and the momentum of that is 1 kilogram times 6 meters per second, or about 6 units of momentum. So before the collision happens, we have 6 units of momentum. Now, if we assume it's a piece of putty, then what that means is that after the collision, the putty is going to stick to the bowling ball, and the putty and the bowling ball are going to move off together as one object. And so when we look at that calculation, we know that the interaction, the collision, is happening inside our system, so momentum must be conserved. That means that the momentum after the collision must be the same as the momentum before the collision. Well, again, we know the momentum before the collision was 6 units in the positive direction, and now we have a 6 kilogram object, right? The putty and the bowling ball together now, sticking together, have a mass of 6 kilograms. So the question is, if I take the 6 kilograms and multiply it by the velocity after the collision, I should get 6 units of momentum. Well, that's pretty easy math for you, I hope. And you can see that the velocity afterwards in this situation is 1 meter per second. So in this particular case, if the piece of putty, the 1 kilogram piece of putty, or if the 1 kilogram object were a piece of putty, the bowling ball after the collision would move off to the right at 1 meter per second. On the other hand, if we assume that it's a piece of super ball, if it's a rubber ball that bounces backwards very efficiently, and it moves backwards after the collision at 4 meters per second, then when we go to solve the problem, we still know momentum's conserved. That's not changing, but the type of collision we have is. And so after the collision, we now still have two objects. We have a super ball and we have a bowling ball, and they go their separate directions. So when we add up the momentum of the super ball after the collision, we're told that it's a 1 kilogram piece of, or 1 kilogram super ball moving 4 meters per second towards the left, which of course is a negative velocity. Again, signs matter here. The 5 kilogram bowling ball is going to move presumably to the right at some final velocity that we don't know yet, right? We're trying to figure that out. But we do know that if we add the momentum of the bowling ball to the momentum of the putty, we should get an answer of 6. We must get an answer of 6. So simplifying the math a little bit, we have minus 4 plus 5v equals 6. Add 4 onto both sides, that gives us 5v equals 10. Solve for the velocity after, and we get an answer of 2 meters per second. So in the case of the 1 kilogram object bouncing, okay, once again, it's going to carry some momentum back to the left in that bouncing process, which actually increases the velocity at which the bowling ball moves to the right. So if we want to move the bowling ball efficiently, and get it moving as quickly as possible, we actually have a better process for getting it moving to the right with a bouncing type collision, right, than we do with a sticking collision. So bouncing puts a bigger momentum change on the object than sticking. Okay, and again, we talked about that some when we talked about collisions with vehicles, and we said you really do not want a bouncing collision when you have a collision with your car. You really want to have a stick, a crunch and stick situation where the velocity goes to 0 as quickly as possible. We want to dissipate the energy, and we do not want a bouncing collision. Okay, again, I'm not going to collect this since you're watching these videos independently, but let's practice another problem here. Let's suppose Darren, who has a mass of 45 kilograms, runs and jumps off a stationary 168 kilogram floating platform on a lake. Darren's velocity as he leaps is 2.7 meters per second. Ignoring any frictional effects, what is the recoil velocity of the platform? In other words, this floating platform is able to move back in the water freely when Darren jumps off. And so pause your video and think this problem through, draw a little sketch, work it through, and then restart the video to see how you did. Now, the correct answer is minus 0.72 meters per second. If you're not sure how we got that, I will help you through the problem right now. Here we had a 168 kilogram platform that Darren was standing on. And so Darren has a mass of 45 kilograms, and he is going to stand here. And so initially he's just standing on the platform like this, and his mass, of course, is 45 kilograms. So that's kind of our initial situation. right? And the final situation, we have the 168 kilogram platform moving presumably to the left, okay, to conserve momentum at some final speed we'll call v. Darren, on the other hand, after he jumps, he will have jumped off the platform, okay, maybe trying to dive or whatever. He's still 45 kilograms, and he jumps at a velocity of 2.7 meters per second. So that is our final picture here of what's happening. So when I look at the initial momentum in the system, it's not hard to see with both the platform, which is floating in the water, and Darren, okay, both of them still, that there's no momentum in the system. P initial is 0 in my system, okay? Notice there's no ropes or wind or anything like that in this problem. It's just an interaction happening inside our system. Again, if it helps, you just can draw a big box around your system and say, okay, did anything really come in inside that box or outside that box to interfere with things? And the answer is no. It's an interaction happening inside our system here. And okay, so when we go to solve this, we know that momentum has to be conserved. So we know the final momentum in the system after Darren jumps has to be 0. We know the answer. And so what do we have? Well, we have 168 kilograms, which is standard units, times the final velocity of the floating platform, plus the mass of Darren, 45 kilograms, times his velocity of 2.7, which is in the positive direction, the way I set up my picture. And that has to all sum to 0. So when we pull out our calculator and we do the math on this, you can double check me on this, but we get a velocity here of about negative 0.72 meters per second for the velocity of the platform after Darren jumps off of it. And so you can see how this is a very important strategy for solving problems. So we want to also talk about collisions today. And there's collisions that happen not only between cars and between people and things like that, and objects that we look at, but it's all throughout throughout nature as well. I mean, sometimes even other animals collide, and here you see a couple of bees flying towards each other, and they actually accidentally collide midair. And so this idea of collisions is not just something for engineering, but it's also important for science and understanding collisions that can occur in nature. And there's two basic categories or general classifications, okay, for collisions. Okay, one type of collision is called elastic, all right, and the other is called inelastic. Okay, now most of the time, the type of collision we get is probably somewhere between elastic and inelastic, probably much like these bees that are colliding in this video, right? They're not perfectly bouncing off each other, which would be elastic, but they're also not sticking together entirely, which would be inelastic. So in order to actually model collisions, we need to know a little bit more about them, about how much they might have stuck together. So when we're first learning this, what we're going to do is we're actually going to stick with situations where the objects collide in such a way that they're perfectly elastic, they bounce off of each other with no loss of kinetic energy, or we're going to have them collide in a way that they're perfectly inelastic. That is, where they collide and they stick together completely after the collision. So it's important for us to understand the physics that goes along with these two extremes. And so the first one here that we're talking about, of course, is these perfectly elastic collisions. And perfectly elastic collisions conserve both momentum and kinetic energy. So examples of perfectly elastic collisions, probably the closest we're going to come to in the macroscopic world that we live in is maybe like billiard balls colliding, although that's not perfectly elastic, and super balls, maybe two super balls bouncing into each other. That's probably about as close as we can come in the macroscopic world, because most of the time there's a little bit of energy dissipated in the collision process. Now, down on the atomic level or molecular level, air molecules bounce into each other and atoms bounce into each other, and they tend to bounce many times very, very efficiently, and we can model those as perfectly elastic. So, but anyway, if we're dealing with things like the billiard balls or super balls, we generally will model them as being perfectly elastic And again, with perfectly elastic collisions, we conserve not only momentum, but we also conserve kinetic energy. With inelastic collisions, if they're perfectly inelastic, okay, if the objects actually stick together completely after colliding, we call that perfectly inelastic. And notice in this case, momentum is still conserved, okay, but kinetic energy is not conserved. It is not conserved. And if you're looking at that and you're going, wait, how can energy not be conserved? Well, notice I did not say that energy is not conserved. The kinetic energy is not conserved. That is, the final kinetic energy after a perfectly inelastic collision is going to be less than the initial kinetic energy in the system. So some of the kinetic energy disappears, but of course we know energy doesn't really disappear. So the kinetic energy change, that energy actually goes into making sound, heat, light, other forms of energy. Okay? The important thing is to realize that the kinetic energy is not conserved, so we can't use that equation. We can use the fact that the momentum's conserved, but what do we use for our other second fact? Well, the thing is, if they stick together, if the objects actually stick together, then obviously they move off with the same velocity. So if we have two objects, objects 1 and object 2, then object 1's final velocity has to be the same as object 2's final velocity if they are actually sticking together and moving off together after the collision. Okay, so our two equations that we use for perfectly inelastic collisions are the fact that momentum is conserved and the final velocities of both objects are the same. Okay, examples of perfectly inelastic collision would be like perfectly deflated basketballs colliding perhaps, or a clay ball colliding with a wall. You know, that is certainly going to just stick together. Anything where the objects would kind of hit and stick. And again, what we'd really like for our automobile collisions is we'd really like a perfectly inelastic collision. That's what the engineers are shooting for with car collisions. Now, just one more time, in case you didn't hear me the first time, the final kinetic energy is less than the initial kinetic energy when an inelastic collision occurs. Okay, perfectly inelastic collisions can have fairly dramatic kinetic energy changes sometimes. But of course, the energy is not really lost. It's transformed into other forms: heat, sound, maybe light, deformation of the objects. I mean, if it's a piece of clay that collides, then maybe the shape of the clay changes. Of course, that doesn't happen on its own. That takes energy. We have to do work on the clay to change its shape. So some of the kinetic energy may go into changing the shape of the objects, like dinging your car fenders. Okay, so the important thing here is that the kinetic energy at the end of a perfectly inelastic collision is not going to be the same as it was at the beginning. Let's take a look at a simple example here. Let's suppose I have two little train cars and they have magnetic latches on them, okay, so that they will couple together if they get close to one another. Just to keep the numbers simple, let's suppose the one object has 100 kilograms of mass and is moving to the right at 1 meter per second. And the other object, we'll say object 2 here, is moving to the left at 1 meter per second but has 300 kilograms of mass. Okay, after the collision though, they're going to couple together. So they're going to become one 400 kilogram object moving together after the collision. Okay, this is an example of what we call a perfectly inelastic collision. So let's look at some of the math of this. Initially, looking at the momentum in the system, adding up the 100 kilogram object carrying 1 unit of velocity to the right in the positive direction, we get 100 units of momentum. And then we have the 300 kilogram object moving at 1 meter per second to the left in the negative direction, so it has a negative velocity, which means we end up with 300 units of negative momentum. When we add those together, we find that the total initial momentum in the system is minus 200 units. Okay, after the collision, we know momentum is conserved. Momentum is conserved in all collisions, right, whether they're elastic or inelastic. So momentum, conservation of linear momentum, is your first rule that you want to go to when you have a collision process. Okay, in this particular case, after the collision, we know we still have to have 200 units of momentum, but we now have a 400 kilogram object moving at some final velocity v. So the question becomes, 400 times what velocity will give me negative 200 units of momentum? And solving that out, obviously the velocity after the collision is going to be negative 1/2 meter per second. So these two vehicles here, these two train cars that couple together, are going to now move off to the left after the collision at a half a meter per second. Okay, that's what the momentum, conservation of momentum, and the fact that they stick together after the collision, that's what nature demands. Okay, now if we look at the kinetic energy, looking at the kinetic energy in the system, initially the kinetic energy in the system for car number 1 is 1/2 mv squared, and then we add up the kinetic energy of car 2, which is 1/2 times its mass times its speed squared, and we get 200 units of 200 joules of energy, of kinetic energy in the system before the collision. After the collision, the objects are one 400 kilogram object, and they only move at a speed of 1/2 a meter per second. 1/2 times the mass times the, actually I'm putting velocities in there and squaring them. I really should be putting speed in there, but obviously if we take a velocity, it's negative, and we square it, it becomes positive anyway. So that's okay, the way I'm doing that, but really this should just be speed in here, not velocity. 1/2 times the mass of the object after the collision times its speed squared gives us only 50 joules of kinetic energy. So notice that we started with 200 joules of kinetic energy. After the collision, only 50 joules of kinetic energy in the system, and we notice it's not conserved. But of course, the kinetic energy didn't disappear altogether. It converted into other forms of energy, probably some sound, some maybe some bending of metal, who knows, maybe a spark, heat, we're not really sure, but it dissipated in other forms of energy. Here's a question that you can pause the video and read and try for yourself, and then see if you can get the right answer. It's one of the 5 listed below, multiple choice answer. See if you can get the right answer, and when you think you have it, press play and see if you got the right answer. Well, how did you do? Hopefully you got the answer of 2.99 times 10 to the 4th meters per second. And if you were on the ball, you realized that, well, wait a minute, the Earth was moving at that same velocity before this collision, so it seems like nothing happened. Well, keep in mind here, the reason it seems like in this particular inelastic collision that nothing changed is because if you look at the mass of the object, okay, the mass of the asteroid, even though it was moving at a fairly high rate of speed, it doesn't have much mass, and so the momentum of the asteroid hitting the Earth didn't have enough momentum to really make a difference in the overall momentum the Earth had from the very start. And so, you know, it's a question of relative size of things. So the right answer here is not exactly 2.99 times 10 to the 4th meters per second, but it's so close to that, it might as well be, at least to multiple decimal places. The velocity of the Earth is not going to change from this collision. Okay? Now, let me show you the uh, when you solve problems and you don't put in numbers right away. Of course, we talked about how it seems harder at first, and oftentimes it is. I mean, doing problems algebraically can sometimes be more difficult because you can't, you know, combine things into one number and so forth. And so, you know, you might have pages and pages of algebra to solve a problem. But the advantage of solving it with the algebra and getting the answer at the end in variable form is that you now have a little cookbook formula for the answer to that question. Okay, so let me give you an example of this. Let's suppose we want to work on this one-dimensional, perfectly elastic collision, okay, where both objects are in motion. Okay, we haven't done one of these yet, I don't believe. And so we're going to deal with a situation where this ball here is 2 kilograms moving to the right at 2 meters per second, and it's going to collide perfectly elastically with a 6 kilogram ball, right, moving to the left at 3 meters per second. So we have a red ball and a blue ball heading towards each other at different speeds with different masses. They are going to have a direct, one-dimensional, perfectly elastic head-on collision. And we know from practical experience that they're going to bounce apart like this. We're going to have a boing, and they're going to bounce apart. And what we want to try to do here is use our laws of physics to figure out what the final velocity of the red ball will be and what the final velocity of the blue ball will be. Okay? We actually have enough information to do this because we have two rules that we know are working with perfectly elastic collisions. First of all, we know momentum is conserved, right? And secondly, we know kinetic energy is conserved with perfectly elastic collisions. So when I take the math of this situation, I take the red ball times its initial velocity plus the blue ball times its initial velocity. I get an initial momentum of minus 14 units. That means that the final momentum in the system has to be minus 14 units as well. And I can write the final momentum of the system as being the mass of the red ball times its final velocity, which we're looking for, V1 final, plus the mass of the blue ball, 6 kilograms, times its final velocity after the collision, which is V2 final. So that's one thing I can do. I can write the initial and final momentum, and I know that this has to be equal to this, right? So this equals that. I also know that the initial kinetic energy of the red ball is 1/2 times its mass times its speed squared. If I add that to the initial kinetic energy of the blue ball, 1/2 times its mass times its speed squared, I get the total kinetic energy in the system before the collision, and that ended up being 31 joules. If this is a perfectly elastic collision, then no energy is lost, no kinetic energy is lost, and therefore at the end of the collision process, if I add up the kinetic energy of the blue ball and the red ball, they should equal, I should have an answer equal to 31 joules. Okay, and so these two statements have to be true. Now we can simplify those equations, and assuming everything's in standard units, we can summarize the first equation like this, and we can summarize the second equation like this after we do a little bit of math and simplification. Now we have two equations with two unknowns. Yay, we can solve that. All right, so we take equation 1 and we solve it, and we find out that equation 1, we can solve it and say, well, V1 final, we can't solve for it exactly yet, but we do know V1 final is equal to minus 7 minus 3 times V2 final. We can now take that and substitute that in to this equation for the energy, and when we do that, we end up with this equation right here, okay? And then we continue to do, and we have one equation now with one unknown. That's what we want, one equation with one unknown. That is the way to go about solving a problem, right? Because we know we can get a numerical answer now. So we continue with all this algebra, right? We get a quadratic equation, and we have to break it down and use the quadratic formula. And when we get the quadratic formula, we find out we have two possible answers for V2 final. Either V2 final is minus 3 meters per second, or V2 final is minus 1/2 meter per second. They're both negative. Well, I know that the original velocity for object 2, or I'm sorry, V2 final here, object 2's final velocity, I'm being told that it's actually to the left, so they do not bounce the way I initially thought. Object 2 is going to be moving to the left, if I did my math right. But I don't know whether it's going to be moving at minus 3 or whether it's going to be moving at minus 1/2. So what do I do? Well, now that I know the velocity for object 2 is one of these, I can now take these and test them in my equation for V1 final. I have to try using minus 1/2, and then I have to try using minus 3 and see which one gives me an answer that's possible. So when I go ahead and I substitute this in, if V2 final is minus 3 and I plug that in, I end up with V1 final being equal to 2 meters per second, positive. Well, if I'm thinking about this properly, how could object 2 be moving to the left with a negative velocity of 3 meters per second after the collision, and object 1, the red ball, be moving to the right at 2 meters per second? That's not possible because they would have had to have passed through each other, right? The balls would have had to pass through each other, and I know that's not what happens on a macroscopic level. Objects do not pass through each other. So that can't be possibly right. Physically, that cannot be possible. So obviously, now if I try V2 final is minus 1/2 and I plug it in, I find V1 final is minus 5.5, and that could happen. I could end up with the blue ball moving to the left, right? The blue ball could be moving to the left here at minus 1/2 meter per second, and I could have the red ball moving to the left at an even faster rate of minus 5.5 meters per second. That is possible, and so that is our answer. It turns out the red ball moves to the left at 5.5 meters per second, and the blue ball is moving to the left at minus 1/2 meter per second. Both balls move to the left. Why? This one had so much more momentum, it overpowered the momentum of the red ball in such a way that both balls end up moving to the left after the collision. So you can see this turned out to be a fairly complicated problem and lots of work. Well, what if we had solved this whole problem just using M1, M2, V2 initial, V1 initial, and did not put numbers in? Guess what? It would have been an even bigger mess, the algebra. Okay? It would have been an even bigger problem and would have taken even longer. It would be pages and pages of algebra. The difference is we would have ended up with some nice little cookbook equations that will work for any two perfectly elastic, one-dimensional head-on collision. And we see those on the following page. Okay, so what we see here on this particular page is we see these equations that I'm putting inside this yellow box. Okay, these are very important equations. These are equations that were derived by someone else that went through a very hard process, a very long, painstaking process of algebra, and solved the generic version of this problem. They assumed that you had a mass m1 moving at v1 initial, and it collided with mass m2 moving at v2 initial. And they went through and solved it out for what the final velocities of the red ball and the blue ball would be after the collision. Okay, so in other words, you can use any values now. In other words, you never have to solve that problem again. That problem we did in the last couple pages has been forever solved, and the answer is exactly what is shown here with these expressions. Okay, and so again, it would have been a lot of hard work for you to do that, but if you had done it, you would arrive at these answers. So be thankful. I mean, somebody's already done it, so these answers or these equations right here are very useful. Make sure you have them ready to go for your final exam. And so as an example, in our particular case here, the problem we did on the previous page, we had M1 was equal to 2 kilograms, right? And M2, the blue ball, had a mass of 6 kilograms, all right? V1, the red ball, V1 initial, excuse me, V1 initial was moving at 2 meters per second. It was moving to the right, which is the positive direction. So again, signs here matter. Signs here matter. Okay, V2 initial, the initial velocity of the blue ball, was 3 meters per second to the left, so it had an initial velocity of -3 as far as our x-axis goes. So when we go ahead and take these equations, or take these values, right, if we take the values here for the masses and the initial velocities and plug them into the, all four of those values into these equations and solve it out, what we find is that we get an answer for V1 final that matches up perfectly. V1 final up here, you'll notice if I do the math, I plug it into that equation, it takes me right to the answer of minus 5.5 meters per second. I don't even get two possible answers. It just takes me right to the final answer. If I plug in the values into the equation for V2 final, as shown right here, I get the answer of minus 1/2 meter per second for the final velocity of the blue ball. So what I find is that by using these cookbook equations down here, now the problem becomes very simple. Instead of the last couple pages of all that messy algebra, I simply go right to this cookbook equations and I get to my answers very quickly and efficiently. And that's the advantage of solving problems with algebra and variables to begin with. It may be more work that way initially, but then you never have to really solve the problem again. Somebody can change numbers on you, right? Change initial velocities or masses on you, and you don't have to solve the problem again. You just go right to your cookbook equations and plug and chug and get your answers very quickly. So I hope that makes sense. Now, I think we've covered enough for today, so we're going to stop here and we'll pick up here on Friday.